This conference will now be recorded.
ஏதோ சவுண்ட் வருது டங் டங்.
Actually, this writing pad, I think I have to change the this plug. It is actually becoming loose connection. That's why yesterday also that was the problem. That's why my PPT got hanged. Hopefully today it will work. Let me see.
This conference will now be recorded.
So good evening, students. Today we'll be concluding this ray optics chapter. So we had already discussed the previous problem which we had here. Today we'll discuss from this second problem. Okay, so this problem says a monochromatic light is traveling in a medium of refractive index 1.6, n is equal to 1.6. Okay, it enters a stack of blocks. Okay, a stack of blocks. So monochromatic light is traveling in a medium of refractive index n is equal to this. It enters a stack of glass layers from the bottom side at an angle theta is equal to 30, which you see here. And these are actually blocks. So there are many interfaces, like this is one interface, this is second interface, this is third. Like that, we have here m interfaces. Okay, because we have stacks of layers of glasses, and it is very interesting to see that the refractive index of each layer of the glasses actually different. Okay, that's why there is an interface, and as you go higher and higher, the refractive index actually is getting reduced. Okay, so the formula with which this refractive index get reduced is this: n minus m delta n. Okay, where delta n is given as 0.1, as you see in this figure. So the interfaces of the glass layers are parallel to each other, and the refractive indices of the different glass layers are monotonically decreasing as n is equal to m into delta n, where nm is the refractive index of mth slab and delta n is equal to 0.1. The ray is refracted out parallel to the interface of m minus 1 and mth slabs. So this interface, you look, this is m minus 1, this is m minus 1 layer, as you see, and this is mth layer. And in interface, at this interface, when the ray of light is getting refracted ray is actually parallel to the interface. Okay, so the situation over here, if it is mth layer and this is m minus 1th layer, so you look here, the ray is going like this. Okay, after refraction, you see this is becoming 90 degree. So angle of refraction is becoming 90 degree. That means what? This angle must be theta c, some theta c. So that is what is the case. So at this particular interface, it is becoming, sorry, here it is becoming angle of incidence. If I take this one is angle of incidence, this is actually theta c, and that's why it is becoming parallel to the, or it is actually tangential to the interface. Okay. Okay, all right. Now the question is the ray. Okay, fine. Then we have to, what is the value of m? We have to find out what is the value of this m. Okay. So how to solve this problem? Actually, this is a very simple problem. If we look the very first interface, okay, because uh, we know here it is uh, angle of incidence we know. So if we apply the Snell's law, okay, Snell's law, where I'm applying between this and this interface, okay, this particular interface. So how do I write that? So applying Snell's law, Snell's law. Look for the first this, we know this is n sine theta is equal to nr. Oh, sorry, it will take nm sine theta refracted angle. Okay, we are just thinking this as in angle of incidence, and this theta r is angle of refraction. Okay, if we just think this, then look, this is 1 point, n is given as 1.1, sorry, 1.6, and sine theta is again 30 degrees. So sine theta means sine 30 degree, that is given. And on the right hand side, see, nm is here, so 1.6 into, sorry, 1.6 minus m into 0.1, which is the value of delta n, into sine 90 degree, because angle of refraction is, so suppose this is theta r, so theta r is 90 degree. Okay, according to the condition given. Now look what we can write this. So this is half, right? 0.8. So 1.6 by 2 means 0.8. Again here, this is sine 90 means 1, right? So we know this is like this. Now see, what we get is 0.1 m is equal to 0.8. So which further implies that m is equal to 0.8 by 0.1. What does that mean? This means m is equal to 8. M is 8. Okay, so this is the answer here. Actually, this question is from JEE Advanced 2017, and we have to find out the value of m in integer number. Okay, so here m is equal to, therefore m is equal to 8. Okay, all right, we'll go to the next problem. Okay, now here in this problem it is said that the sunlight of intensity 1.3 kilowatt per meter square is incident normally on thin convex lens of focal length 20 centimeter. As you see, if I say this is the lens, and it has focal length 20 centimeter over here. So sunlight means parallel rays are coming from far, and see, after refraction through the lens, they will actually converge at this point. Then again it will just go like this. So the question is here that ignore the energy loss of light due to the lens. So lens actually absorbs some energy, light energy, but if we ignore that loss due to the lens, assume that the lens aperture size is very smaller than the focal length. Lens aperture size is smaller than the focal length. So in that case, average intensity of light in kilowatt per meter square at a distance 22 centimeter from the lens from the other side is. That means you have to find out what is the average energy density or average intensity of the light. Average intensity of the light at a distance 22. That means this much is 20, this much again 2. So average intensity of light in this unit, kilowatt per meter square, at a distance 22 centimeter. Oh God. 22 centimeter from the lens you have to find out. Okay. All right. So this is the question. Look here. We know what is the intensity. Generally, intensity is intensity. If I write I is actually power by area. Okay, that is what it is. Okay, power by area. If I just okay, power by area. All right. So here it is already given. Power by area is given. See, this is given on this side when it is getting incident or on either side of the lens. Okay, other side. So when it is incident on the lens, then the intensity is given. Okay, intensity is given. Suppose this is a incident. Okay, you have to find out the intensity of the light after refraction at 20 centimeter distance. Okay, that is the question. All right. So here what I'm doing is that see, if I say this is R, capital R, that is the aperture of this uh, lens. Actually, see, this area is what? See, if I want to find out intensity of light at certain point, like certain distance from the lens, so I need to find out the area through which the rays are actually going after refraction. So through that area, actually, if I say this is the area at 20, this is actually 20 centimeter focal point here, and this is the area through which the energy has to pass, and with respect to this area we will be able to find out the intensity. Okay, this area for the incident ray, actually this area has been taken. Okay, this area or the so this is the area. Now from this figure, see, from this figure we can do one thing. What we can do is we just say this is from lens to this one. This is actually focal length 20 centimeter. So I can do, see, from similar triangle, this and this, we can write that, in fact this also I can take, this also. So I can write r by 20 is equal to small r by 2, small r by 2. So if required, I can find out the ratio capital R by small r, sorry, small r by capital R is to be 2 by 20 or 1 by 10. Therefore, the area of the refracted ray and area after refraction AR and area at the in for the incident ray AI, this ratio can be obtained actually, because we know pi small r square, kind of that. Okay, so this also will be pi capital R square. So if we, so this means this is small r by capital R whole square. That means it is 100, 1 over 100, right? This we know. Now look, if we want to find out the intensity at 22 centimeter away, so this is 20, then this is 22. All right, so the intensity of the refracted ray is actually power divided by AR. Okay, that is what we have to find out. We can just do one trick. What we can do is we can write P by AI. This is already given. Okay, P by EI is already given. So this is actually given as 1.3. Okay, this is given. So ratio of the square of the area we will write here. So if this is this, look here, this can be written P by this AI. If I replace, see, A R by AI, this one. So AI can be replaced with 100. Okay, so what is AI? Let us write. AI is actually 100 by AR, or 100, sorry, 100 into AR. Okay, just a minute. So AI is equal to 100 into AR. Okay, so this is what we got. Now in the place of AI, if I write this, see, it will be 100 AR is equal to 1.3. Okay, so this is the thing. Now one more thing is that this P by AR is itself, it actually the intensity after refraction. Okay, so I have to just multiply 100 along with this. 100 over here. That means 130. So 130 will be the power so the question was that what is the power at a distance 22 centimeter from the lens. So we have got it here, P by AR. AR is the area of at this place. Okay, so this is 130 kilowatt per meter square. Okay, so this is how we have got an integer number. All right, we'll go to the next question. So this question is very interesting, and it says an object is at a distance 20 meter from a convex lens of focal length 0.3 meter. Okay, so if we have a convex lens like this, so the object is at, suppose here, so it is at, the object is at 20 meter from the convex lens. Now it has focal length 0.3, so let us say it is somewhere here. So if the object, okay, let us read further. The lens forms an image of the object. Very fine. Obviously it will make an image. If the object moves away from the lens at a speed of 5 meter per second, the speed and the direction of the image will be what out of these four options? I'm not reading each options. We'll just try to solve it. See, the question is, in one sentence, the question is that if the object is moving with speed VO 5 meter per second, then the image formed on the other side of the lens will also move. But what is the speed of that image? You have to find out that. This is the question, and also the direction you have to find out. Okay, first of all, let us see what is the equation of lens. We know equation of lens is 1 by V, that is the image distance, that is minus 1 over object distance, and that is equal to 1 over F. F. Okay, so this is the lens equation we know very well. So to solve this problem, or to find out the velocity of image, we have to use a nice trick and see how we can get it. If we just take time derivative of this equation, see, focal length is always fixed. Only when the object is moving, that means the position of the object changes. If the position of the object changes, then obviously the position of the image also will change. So then what we can do, we can just take derivative with respect to time, this particular equation. So look, this will be 1 over minus 1 over v square into dv dt. Okay, this will be plus 1 over u square into du dt, and this is equal to 0 because this is a constant quantity. Okay, focal length is a constant quantity, right? Now look, this one, this is object's velocity and this is the image velocity. So velocity of image I have taken as vi. If I write this, I'll write vi by v square minus sign here, and this will be plus sign. So let us say this is v object, velocity of object, and that is u square. Okay, u square. This is equal to 0. That means we have got, see here, if I solve for vi, then we have uh, v square by u square into vo. All right. So this is what is the formula for finding out velocity of image when the object is moving with velocity vo. All right. So now we have to find out what is v by u. U we know 20 meter. Okay. Then we have to find out what is v. Then we'll be able to solve the problem. So u is given as minus 20 meter. Okay, focal length f is given as 0.3 meter. Then v is how much you have to find out. So we'll again use the same length formula. We'll put the values. Okay, so here 1 by f is 0.3 meter plus 1 over 20, and it is actually with a minus sign. Now if we solve for 1 over v, this is 10 by 3 and this is 1 over 20, so it will be 60, right? This is 60, so it will be 20 into 10, so 200 minus 3, that means you get 197 by 60, or v is equal to 60 by 197. Okay, this is the thing we have got. This is the image distance when the object is fixed at 20 meter distance from the length in the left hand side. Okay, now look, we have to find out the velocity of image. So v square by u square into vo, this is the formula, right? So we know v square is 60 by 197 whole square divided by 20 whole square, 20 square into 5 meter per second. VO was given 5 meter per second. So look, if we do the calculation part somewhere here, let us say in this case, okay, I don't have space over there. So it is 36005 divided by 197 square into 400 again here. 400 because 20 square is 400. Okay. Now if I just strike this out, this will be 9. So 45 by 170, 197 square. If we do the calculation, we'll see this VI will be actually 1.16 into 10 to the power minus 3. Okay. So look the options here. The D option D will be correct answer for this question. Okay. So 1.16 into 10 to the power minus 3 meter per second towards the lens. Okay, so if the object moves with speed 5 meter per second, it is away from the lens, then the image will move with speed 1.16 into 10 to the power minus 3 meter per second towards the lens. Okay, so towards the lens because it is going away here in this direction. All right, we'll move on to the next question. So this question says the value of numerical aperture of the objective lens of a microscope is 1.25. If the light of wavelength 5000 angstrom is used, the minimum separation between 2 points to be seen as distinct will be how much out of these 4 options? Okay, see here, to solve this kind of problem we need to know what is numerical aperture and how is it related to the separation between 2 points, etc. So I'm writing it here, better remember this. So numerical aperture NA is equal to 0.1 for an objective, for the objective of a microscope. Okay, is this, so 0.61 lambda divided by small d. What is this d? This d is actually d is separation between the 2 points to see them distinctly, to see them distinctly. To see them distinctly. Okay. Now see numerical aperture is given, wavelength is known, and d we have to find out. It's a very simple problem if we know the formula. 5000 angstrom will make it into meter in 10 to the power minus 10 meter, and this numerical aperture is 1.25. Okay, so look here, this is 6 to 1. Let us strike this off. 5 into 10 to the power minus 8, sorry, minus 7. This is in meter. This is 5, right? So not 5, 25. It's 25. Okay. So now 61. So 25. Is it 2? It will be 50. So 1, 1. Again, it will be 400. Okay. So 0. If we take 2 decimals, then it will be 2.44. If we take 2 decimals. Okay. Okay. So 2.44 into 10 to the power 10 to the power minus 7 meter. So if we want to make it into micrometer, then we have to multiply here 10 with 10 and divide this with 10. Okay, divide with 10 and multiply with 10. So 10 to the power minus 6 here. Okay, so 0.244 here actually had been taken 2 decimals. So this is in meter. You can write that the answer is 0.24 micrometer. So this first option is the correct answer for this question. Okay, so we'll stop it here for today because we have already completed like roughly with this chapter. Next day we'll pick up questions from JEE papers, previous JEE papers from some other chapters. So thank you for your presence. Bye for today.